want to talk to you a little bit about routing fundamentals. I want to discuss some of the components about routing that you may already know, and I want to review them. I want to make sure that we are all on the same page when it concerns routing. We're talking about the same terms, the same concepts, and when we refer to things, or when I refer to things, that you understand the same thing that I'm talking about, and there's no misconceptions about what is being discussed and exactly what topic we're talking about. Let's take a look here. We have here a very simple network, if you will, and the idea behind routing IP packets is obviously to take the data coming from this source and, well, delivering it to this destination via means, correct? This source to this destination, or this source to this destination, or wherever it is, and that the way it travels in the middle. The interesting part is this is a very, very simple network. As you can see, there are only 1, 2, 3 routers involved, and there are 2 switches involved. Kind of interesting, isn't it? And we have a few networks here. We've got a network 192.168.2.30. Then we have a 3.0, a 4.0, and a 5.0. And we need to get data from 2.0 over to 5.0. And in this particular instance, it's going to go through 1, 2. Well, it's going to go through, 1, 2, 3, 4, 5 hops, if you will. 3 router hops, right? And then a couple of switches to reach its destination. This data, as it's traveling through the network, needs to be delivered needs to make sure that it's reaching its destination. The IP packet needs to get from this location over to this location reliably. It's interesting that in the routing universe, we consistently think about packets being sent and packets being delivered. Sometimes you get so lost in the forests and trees that you fail to realize that behind those packets, behind the data and the packets that are being delivered and the switches and the routers are actual applications that are running, that are relying on these packets being delivered correctly. It's not simply good enough to say that, oh, we have 80% success rate. And 80% success rate, you and I both know, is not sufficient at all. 99% success rate is okay. You need 99.9% or better. Isn't that true? Can you imagine 2 out of every 10 packets falling apart, getting lost in the shuffle, and not being delivered at all, no retries taking place? That would be detrimental. So here we've got a few routers that are doing their jobs, here, here, and here, and we've got our switches doing their part as well. The other thing that I wanted to talk to you about is keep in mind this whole getting from network 2.0 to 5.0 and the networks 3 and 4 in between to gain access to network 5 requires, behind the scenes, a whole lot of work, because this may not be in the same building at all. These are different networks altogether. It's very possible that this network that you're looking at right over here may be located, let's say, may be located in New York City, and this network right over here may be located somewhere in Queens. Maybe this network over here is located somewhere in the Central Park area. Yes, all New York, right? Maybe this network right here is located somewhere in Long Island, right? So, and what I really mean to say is very possible that this data is traveling through some very complex behind-the-scenes networks to reach its destination. And not to confuse or not to undermine the fact that these cables right over here, these cables can be very long and very lengthy. Who's to say that this is all part of New York and this entire network takes place in New York and the surrounding New York areas? And who's to say that this network is not going from one end of a city or state boundary over to another. These networks can be located anywhere, right? They can be located in any part of the city, any part of the world, but we are normally not willing to wait any more than a fraction of a second for the reply to get back to us. It is very possible that if we see the network, that this particular network, let's say, if it's located somewhere in China and we're located in the US, it's possible we're willing to wait a little bit to be able to gain access to the resources on that network, but we're not generally willing to wait any longer. We're going to try and look for an alternate means of getting to that resource. It is also very possible, well, very likely, that to get from the US somewhere in New York City over to China, let's say, is going to require a lot more than 3 hops. Very possible that that's going to be the case. As a result, the data doesn't only need to reach its destination, but it needs to come back. This is also something that is sometimes misunderstood or not completely understood by many of the network admins, if you will. The data that travels, it's a two-way street. You not only have to get the data to the destination, but the destination has to reply to you. It's a two-way street. So this round trip that goes over to the server and comes back has to be very, very responsive and very reliable. You want to make sure that when you're contacting, let's say Google, that the data not only reaches Google, but it also comes back and replies to you. There's another interesting aspect when we're sending data. We're talking about the internet, so I might as well talk about the internet. When you go to google.com, let's say, or when you go to amazon.com, let's say, or whichever website you want to go on, a lot of internal entries, a lot of other related sources are accessed as well. For example, Google or Amazon or any website that you go on are going to have ads. So when you gain access to Amazon and it goes through its routing and whatever it does to gain access to the Amazon's website, what ends up happening is that Amazon may say, I got a user that is on my network. I need to tell them about these specials. I need to tell this particular user about these other sites, about these other tools, about a word from our sponsor. I need to tell this particular user about the weather-related warnings or travel-related alerts because this user is located in a part of a country or part of the world that is having weather-related issues. Or maybe Google's going to say, you are located in this particular city. I need to inform you about late breaking news that's happening. And as a result, your source is going to go to other sites to meet the needs that is being pushed down to you by the server. All of those things are packets being transmitted back and forth to and from the source, to and from the destination. And the destination changes shape all the time. So let me give you an example. When I open up, I'm going to open up Google here. And when I open up Google, you notice that Google shows up, no big deal. But I'm going to take a look a little bit under the hood. Here is network. And I'm going to record right over here. I'm going to enable network traffic capturing. The way you gain access to this bottom layer in Google is Internet Explorer is by pressing F12. F12 enables and disables this feature. And when you click on this network tab and you select capture network and you go on Google again, watch what happens. Look, it tells you about everything that it did and everything that it contacted along with the sites that it went on, the protocol that it used, the method that it used, the result that it got, the type of code, in this case JavaScript that it executed, HTML code that it executed, and so on. And it also tells you about the timings, how long it took to reach its destination. For example, it says that it took 312 milliseconds. That's why it's a little bit higher. And this one took 343 milliseconds, and so on. So you can see where the faults are or where the problems are. So you really have to be sure. Here, for example, are console commands, things that I use to send. I executed the www.google.com, and it ran through some code. It ran through some unspecified errors, which I don't really care about because I'm not the one responsible for this code. But I do get to see how it travels. If I end up going to Amazon, you can see everything that it did to get to Amazon.com. And look at this list here. Look at this list. Look at everything that it loaded. Wow, right? So if you really want to think about it, Amazon.com, I just did that, right? all I did is that. Now, if I choose, I can click on details. And you can see that there are 279 different requests that were sent out, as 280, and it just goes on, as a result of me going to Amazon.com. And the reason I'm saying this is, and when I go to Google, and I go to details, it's 1 of 14. Right? A lot smaller range. That's why Google is loading so much faster. But nonetheless, it is executing JavaScript code. It is going and executing other HTML code and brings the data in. It's very, very critical that it's very, very critical that you understand that depending on what source you're gaining access to and where you're responding to, what destination you're responding to, will dictate how quickly the page is loaded. Here's UI responsiveness, and I can select Start Profiling here. I can profile for performance for my user interface. And when I go, for example, on Amazon.com, it is starting to profile my user interface and how quickly it's going to begin to log the information. I can click on Profiler, I can run Profiler, and I can begin to profile everything that's going on in my interface as well, and how well it responds. What does all of this have to do with network? Well, I want to be able to see how it reaches the data and how it reaches the information that I request. It's very important to me to know how the data is being gathered and how, when I go from my source to Google.com or Amazon.com, how it reaches my destination. And everything that happens in the middle, all of the routes that it took, need to be exposed. How do I do that? Well, in Windows, if I go to the command prompt in Windows, let me go to CMD, open it up as an administrator, say yes, and there's the administrator command prompt. And I'm going to do traceroute utility here, www.google.com, and there it is, tracing the route from my location over to all of the hops. You notice right over here, 1, 2, 3, 4, all the hops that it's going to take for it to reach Google.com. And it's going to tell me behind the scenes exactly how many milliseconds it takes and how many hops it takes for it to reach Google. Here's reaching Google. Look at this. We are at hop 7, hop 8. Okay? And it says it's going to route it over a maximum of 30 hops. Right? So here it is, just reach Google on the 7th hop. 9th hop, look over here, it wants to go to 74, 125, 21, 104, which is what Google.com resolved to, where I am at. So here's everything that it's taking for it to get to Google. Here it is, here's 74, 125, 21, 104, and in this particular instance, it took 11 hops for it to get there. Now, it's very possible, there you go, I do it again, and it goes through the same process. Right? It's very possible that depending on where I am, the number of hops that it's going to take for it to reach Google.com, or for example, a different location. So right over here, I'm going to change this to Amazon, and it's going through getting to Amazon.com, and here it is going from, after the 3rd hop is when it gets out, and it goes out and starts to look for Amazon.com. And the number of hops is one of the reasons, this 1 right here, 2, 3, 4, and so on. The number of hops is really going to dictate, to some degree, how long it takes to reach the destination and everything that's involved. It's not necessary that the more hops equals bigger cost, if you will. It is very possible that 6 or 7 hops may take less time than 1 or 2 hops. We're talking about traffic, aren't we? And what is really meant by traffic? Well, it's very possible that this route right over here is very busy, and this route is not as busy, and this route is busy. So just because I'm going through these hops doesn't necessarily mean that all of them are going to be of equal cost. They may be busy at different times of the day, at different hours of the day, and the source to reach the destination, depending on what time of the day and what the location is that the source is contacting this destination, it may take longer or it may be faster, depending on what's being requested. Also, there are some other factors that are associated with speed. Maybe the source is asking for information from the destination about a database record. That means that when the source requests that information, the destination needs to process that data, retrieve the information about the data from the database, and then return it back to the source. Well, there's some processing time involved. It is not all the time that is spent waiting is not all of the time associated with sending the data back and forth. If you say that if I want to receive information from a database that is located on this particular destination, or I want to locate some information about a particular customer, a SKU, a product, an inventory item, whatever the case may be, then you, the source, has to wait for the destination to process and get the data back and send it on its way back to you via the mechanism or via the path that it chooses to send it back to you with. Here's another interesting factor. Routing, as you might be aware, takes part or plays in nicely, if you will, inside of the OSI model. OSI is the Open Systems Interconnecting Model. Here's something that you may or may not have seen. This is an excellent diagram associated with the OSI model. Here, for example, are the 7 layers of the OSI model that you may very well be familiar with. Here they are. And here's everything that's going on at these layers right over here. And these layers are very, very important. It obviously goes from physical layer on the bottom all the way up to the application layer, which is the 7th layer on top. At the physical layer, you want to keep in mind that that is where the physical connectivity is. The RJ45, the RS-232, the 100 or gigabase T, the DSL, 802.11 wireless components, all that happens at the physical layer. It's at the data link layer that you have the MAC to LLC conversion, MAC to the logical link control. MAC addresses are sent from the physical to the data link, and logical link control, or LLC, is the one that ties or binds the data link to the network layer. Other protocols, if you will, such as frame relay or HDLC, or token ring or PPP, point-to-point protocol, or fiber channel, all of these are located at the data link layer. It is at the network layer that you actually end up seeing the IP protocol, the IPsec protocol, the ICMP, IGMP, OSPF. All of those are located at the network layer. The first 2 layers of the OSI model on the bottom there are known as physical network addressing, if you will, or physical addressing associated with devices. From layer 3 up is referred to as logical addressing, because it is from layer 3 up that you're dealing with the IP-based protocol. You're no longer dealing with MAC addresses. You're no longer really dealing with the RS-232 or RJ45 cables or 100 base or gigabit or gigabit-based TX transmission cables, or the wireless adapters, if you will, the physical wireless adapters, the 802.11 series or 802.1, 02 for token ring, 03 for Ethernet. You're not really dealing with that. That's all at the physical layer. At the network layer, you're dealing with the IP protocol. It is not until you get to the transport layer that you're dealing with the TCP protocol or the user datagram protocol or SCTP or the secure sockets layer or the transport layer substrate. The TLS layer, the transport layer protocol is dealing with the transport layer of the OSI model is dealing with these protocols and many more. It is not until you get to the session layer or the session presentation and application that they're referred to as the upper layers of the OSI model, and it is at these layers that you're dealing with sockets, you're dealing with session establishment, you're dealing with remote procedure calls and name pipes. It is not until you get to the presentation and application layers that you're dealing with the HTML or the JPEG, or you're dealing with FTP or Telnet or DNS or DHCP, which is not listed here, or SMTP, or HTTP and the World Wide Web and email and point-to-point post office protocol and file transfer protocol and your MP3s and your AVIs and your JPEGs, your movies and your pictures are all dealt with at the session, presentation, and application components. Here, for example, it explains what's happening. At the physical layer, right over here, you're dealing with media and the signal. You're dealing with the binary transmission of data. At the data link layer, you're dealing with the physical addressing. This is where the MAC addresses reside, if you will, the physical addressing of the components. The router's MAC address is really what you're dealing with. In the network layer, right over here, is where you're dealing with path determination and logical addressing. Logical addressing is another way of saying IP-based addresses. Routers come into the picture at the network layer. At the data link layer, you're dealing with switches. Okay, you're dealing with switches at the data link layer. You're dealing with routers at the network layer. Routers are the ones that are going to determine path, and logical addressing or IP-based addresses come into picture in the network layer. It is at the transport layer that end-to-end connections and reliability of the delivery is guaranteed. So data that is going from the source goes over routers and is delivered to the destination in this manner. Transport layer, in other words, the TCP protocol, and the TCP protocol, the UDP protocol are the ones that guarantee end-to-end reliability. Then you have the session layer, which talks about the inter-host communication. When you're using inter-host, when you're using remote desktop from a source to a destination, session layer comes into play. At the presentation layer, there is a data representation and encryption that is taking place, data that is encrypted and gathered and unencrypted. The encrypted data is sent, unencrypted data is received, and data is represented inside of your application. The presentation sends the data over to the application layer, which is a network process to deal with the application. The data is presented to the application. For example, here is talking about Google. So when you send the data from your physical device, your network adapter, all the way up to the point that it reaches Google, and everything that happens in between is clearly represented inside of the OSI model. So when we're talking about layer 2, and we're talking about layer 3, layer 2 is really dealing with switches. Layer 1 is dealing with the physical aspects. Layer 3 is dealing with network, and in our network, and networking devices with logical layers is talking about routers, transport layer, and the session, presentation, and application upper layers. So that's really something you need to have in mind as well. There's a lot more to follow. Please keep track of this. If you didn't really understand something that I was talking about, go back and review it. Really glad you're here.
Start with new learning now.